get started. Let's get started. So we're lucky to have Dr. Dave Luxat with us today. I've known Dave now for a dozen years, something like that. Yeah, I was going to say about a dozen years.
Yeah.
He got his PhD in condensed matter physics from University of Toronto. So it's a very interesting background to go into nuclear safety. I guess I met him when he was with Jensen Hughes. And if you've never heard of Jensen Hughes, they acquired a couple of other companies and do not only fire analysis, fire safety analysis, but overall safety analysis for many industries, one being the nuclear industry. And I got to know Dave particularly because he was one of the experts using MAP, which is a modular accident analysis package. One of the package or program, which is the industry's version of the Melchor model. And I can tell you more history, other than to say that Dave is absolutely excellent analyst. And then he failed and became a boss. And he now is the manager of the Melchor Nuclear Energy Safety Research Group at Sandia. So without further ado, Dr. Luxat.
Thanks, Mike.
Dave.
Thanks, Mike. No, it's a pleasure to be here. And yeah, I'm trying to remember. We've definitely known each other for a while now. And the crosswalk meeting was certainly one of the first meetings that was really fun way back when, comparing MAP and Melcore. So I just wanted to kind of give an overview of a lot of the work we've been doing at Sandia, primarily recently in the area of nuclear energy safety research, and a lot of it revolves around Melcore. And the MeltCore computer code. And if you will, developing a lot of the technical bases, a lot of the models that actually get put into and housed within what is MeltCore, which is often referred to now as a repository, if you will, of our state of knowledge in nuclear safety and how nuclear energy systems respond under accident conditions. The overall primary use of Melcore and its central role is in characterizing for in the U.S. at least and internationally as well source terms. That is, under accident conditions, how many radionuclides or what is the radionuclide release to the environment as a function of time and as a function of distribution of types of radionuclides. That's the fundamental metric on which we really regulate nuclear power in the United States. So that is there the potential for a public health and safety risk? And is that risk acceptably low? And Melcore is really the code. It rests on a broad range, really by now 40, 50 years of work to develop the understanding of how nuclear energy systems respond under very high temperature conditions, how fuel fails, how radionuclides escape the fuel and transport themselves throughout reactor systems, containments, and ultimately into the environment. This is an overall summary, if you will, of the process that's often used, going all the way from PERTs to experiments, to the modeling of individual phenomena in an integrated fashion in Melcore to calculate across different accident scenarios, the potential for fission product release to the environment. And that ultimately gets synthesized into what is in the light water reactor space referred to as a design basis source term. Melcore.
So can I?
Sorry, Mike. Absolutely.
Can you explain to the audience so they may not know the little box at the very bottom?
Oh, sorry. This one here.
Yeah.
Okay. Absolutely. So this is actually how we typically characterize or group our releases to the environment. We have different phases in our accident scenario. We have fission products when the clad breaks. We'll have a release of fission products, gap release early on, an initial burst of radionuclides. And you can see here that this is really where, in a very brief period of time, about half an hour in an accident scenario, we have a burst of things like noble gases coming out, etc. And then we move into a later stage of accident progression where we start to get the fuel being damaged, it heats up, it melts. You get kind of that 3 Mile Island molten lava, if you will. And here you get a large release out of the fuel and into the containment. 95% of your noble gases get out. Iodine, bromine, your halogens wind up getting out. And then you have things like cesium, those long-lived fission products getting out. And then finally, you get later in the accident scenario, and you have more extensive degradation, and you have more fission products pumping out. Yeah.
Just for my background, this MeltCore, is this for pressurized water reactors, boiling water reactors, can-do reactors?
So here we go. So here we go. That's a perfect question. I'm going to kind of move into that now. Its heritage is in light water reactors. That's where it started. We really started out from 3 Mile Island to resolve critical issues around the safety of light water reactor technology. And all of that research program really got bundled up and put into MelCore as models that can simulate accident behavior and fission product release under these severe accident conditions. So it really is the repository of all that R&D, the experimental R&D model development from it that really started in force after 3 Mile Island. However, MelCore as a code is really, I think I got quoted, I often call it a Swiss Army knife of nuclear energy safety. You have all of these phenomenological processes in MelCore, and they're actually very common across reactor technologies. So aerosol transport, for example, is very common, be it a light water reactor system, be it a sodium system. There are differences that are specific, but the actual phenomena and the modeling of that phenomena is actually buried in MelCore and is applicable across reactors. So MelCore really is a toolbox that has evolved, if you will, now to be applicable not just to light water reactors, but to, frankly, every reactor type out there. It's also used in facility safety assessments. So if you've got a DOE facility or a fuel cycle facility, you can also apply it to look at the potential hazardous release of radionuclides from containment or from confinement in those situations. So it's really a broad.
The only thing I guess I'd add to help Professor Henderson is that if you think of it that way, then the next question you might ask is, well, how do you validate it? And therefore, then you have to go to separate effects experiments and use pieces of MelCore to make sure that the physics you put in actually returns what you see in an experiment. Is that fair?
Absolutely. And so this is essentially just showing, if you will, one view on the evolution. I won't belabor this too much because this is, I think, really what I wanted to just illustrate and get at was MelCore at the end of the day, when we started very early on in after 3 Mile Island, building these types of tools. We started with very, if you will, separate tools that analyzed how fuel heated up, how the thermal hydraulics of the core behaved, and we had these separate codes, and we did our best to couple them. And I wasn't ever involved in that, so but I rest assured everybody has told me that it was a very ghastly experience to couple these separate codes, transfer data around through files, et cetera, et cetera. And it missed a lot of the features of actually capturing how these different phenomena influenced each other, if you will. And so with time, what started out as sort of separate codes began to coalesce, if you will, into a single sort of integrated accident code, which is what MelCore has become. It's what MAP in the industry space is. It's really the earliest example in many regards of a multi-physics code with the fidelity of the physics tuned to, if you will, the level of knowledge in our experimental understanding and the level of knowledge needed to characterize source terms and accident progression. And so MelCore really, when you look at it, and this is a simplification, but it's really evolved generically. It's got a general thermal hydraulics model that can capture not just light water, it can capture helium, it can capture molten salt thermal hydraulics, it can capture sodium thermal hydraulics. And if you've got another fluid with well-defined equation of state, we can plug that into. It captures the fuel thermal mechanical response, not just for light water reactors, but also for high temperature gas reactors, for Trisome. We're moving into sodium fast reactors this year and metal fuels. It also then has a whole bunch of models in there looking at core degradation, looking at how fuel fails, how it relocates, how it potentially melts into these sort of lava-like crucible formations where you get this hot lava of fuel sitting in your reactor core like we saw at 3 Mile Island. And in situations where it progresses more severely, you also then have the potential for it to release into the containment, for the vessel to fail, for the core, this hot lava to breach the vessel lower head here and move out into the containment and contact hot core or concrete, erode concrete, and then you have core concrete interaction. And it literally has all of these models to characterize the entire spectrum of an event with mechanistic phenomenological models. Finally, then, it also has models to look at fission product release and transport. So aerosol transport models. And then recently, as of say, late 2000s, around 2005 to 2010, we added simplified point kinetics models to capture reactivity effects and reactivity feedbacks, because for a broad range of systems looking beyond light water reactors, high temperature gas reactors, etc., there was the need to better understand how accidents could progress that were initiated due to a loss of reactivity control. Sorry, please.
Yeah, you're good. Maybe you'll get into this, but what kind of methods do you guys use, like finite differencing or like finite element or?
So there is a little bit of that. It's not, I would say, there are finite difference calculations in there. The code itself, the thermal hydraulics, is a control volume approach. So it by and large is more of a lumped approximation in most situations. However, when it comes to better resolved physics, be it heat transfer or conduction, be it fission product diffusion in Trisome Systems, we actually do have models in there that do a finite volume calculation. Now, generally, we don't actually need that level of fidelity in most situations because the uncertainties that we're trying to characterize are not due to, did we mesh well enough? We're really trying to characterize uncertainties in really gross behavior of the fuel failed. How did it fail? Do we really know the failure mechanisms of the fuel adequately? Or are the uncertainties in fuel failure broad enough that we need to have a coarser model, but one that allows us to do many more uncertainty studies? We also, to characterize source terms and overall risk, it's more important for us to understand many accident scenarios, not just one accident scenario. So it's sort of a bifurcation or a difference in the use or the need of modeling and simulation tools here. We're interested in evaluating what happens to a system when, if you will, it begins to break out of its bounds. So we all design an engineered system to have very restricted, very confined degrees of freedom. We know how it behaves. A bridge doesn't oscillate like mad, if you will, unless it falls down eventually. We design it in a way to have very restricted degrees of freedom, controlled degrees of freedom. And we often perform and do very detailed modeling and simulation to ensure that it stays within those confines, that the bridge doesn't oscillate like mad, that under the loads, it behaves very well, that under accident conditions, like a LOGA, if we have safety systems come in, we do detailed modeling and simulation to ensure that the performance of the system is constrained, that we stop it from getting out of control, shall we say, or breaking loose of its bounds. When we get into Melchor and analyzing risk, we're really looking at how a system degrades and how basically many degrees of freedom enter into play. And how essentially it behaves when it's no longer behaving within its engineered confines. And there we need much more focus on uncertainty analysis, less on really detailed high fidelity modeling to ensure high confidence that it doesn't exceed its safety limits. So, and that's why, for example,
I guess kind of maybe it's on this point. And
Yeah.
so for a lot of those like design restrictions and everything,
Yeah.
we've always kind of focused that our fuel is going to be solid and stationary.
Yep.
So do we have like the ability to open that up to a salt reactor where the fuel is now moving?
So for our reactivity effects, we actually have developed a point kinetics model and implemented a point kinetics model for flowing fuel.
Gotcha.
Yeah, so that's actually in there. Thank you. We actually just put that in there this last year. I didn't want to go into these details, but we actually did benchmark it quite well against the MSRE. There's a zero power pump coast down test, and it actually benchmarked quite well. Surprising, anyway, I shouldn't say it that way, but it actually captured the key phenomena quite well. Now, Melchor itself, it's this shall we say toolbox of phenomena, of phenomenological models of relevance to accident progression. We're actually, while it's being developed, and I really wanted to make this point, while it's being developed, since the early 80s, really, in many forms, we're actually going through a process right now of modernizing the code, of actually re-architecting the code. And the goal there is we're really trying to open the system up to allow it to more flexibly evolve with time, to allow us to add physics models much more flexibly. One of the key things that you often see in codes that have developed over many years is that there is a lot of, if you will, interweaving of capabilities of functionalities. One of the key things is that you often find numerical solution schemes are interwoven with the calculation of the physics. So if you go back to think of a very simple, mass and energy balance. I've got rates of change for mass and rates of change for energy. And then I've got an ordinary differential equation scheme to integrate that mass and energy rate of change. What you often find in these legacy, well, I should say legacy codes, in these older codes or these codes that have evolved over time is that numerics and the calculation of those rate terms often gets bundled up in the source code all in one place. And it makes it very difficult to, if you want to say, add new rates of change to represent new types of mass exchange processes, new types of energy exchange processes. It actually becomes very difficult to add those because now you've got all this code sitting there to handle the integration of the differential equations. And so we're actually opening this up and separating these out into a much cleaner hierarchy of objects and a much cleaner separation of functionality so that we can open the code up much more flexibly to add those types of phenomenological processes readily. And it's really driving at, and this is a core thing for me, to activate innovation in nuclear energy, we need our methods to evolve faster. We need to understand how our methods and uncertainty in our methods impact any safety decision down the road, any licensing process. If we can't change our methods quickly and investigate the impact, we can't innovate quickly. And so this is really driving at the core, at fundamentally, driving and supporting nuclear energy innovation. And that's the fundamental philosophy and drive. Obviously, there are efficiencies to be gained that are critical from the nuclear energy sector, but this is really the drive. Yeah, there's a lot of cool stuff to be done technically, but the motivation is really again driving innovation. And so while Melchor, and you know, I know I'm jumping in, there's a lot of history with Melchor for light water reactors. And Mike, I'm sorry, but I am a water guy too. But one of the things that we're doing and that we see with Melchor is that it's really a tool at the core that is critical to activating and enabling innovation in the nuclear energy sector. Is the nuclear energy sector going to be a sector that is going to grow or not? And so Melchor, as I was saying earlier with 3 Mile Island, it really worked and it was developed to help us resolve, was nuclear energy safe enough? Is it an acceptable risk for the public to have nuclear energy technology? And we have reached that point where we do understand that the risks are manageable and it's certainly a lot lower than other technological activities. Nuclear energy, though, and the drive is to enable innovation in this country, to solve the critical challenges in our energy system. Under the Nuclear Energy and Innovation Modernization Act, Nuclear Energy Innovation Modernization Act, Congress has directed the NRC to really modernize its regulatory practices, its regulatory approach. And one of the core, and with the focus on licensing non-light water reactor technology. And so the NRC is essentially acting or working under a near-term implementation action plan, with one of the key components being focused on analytical tools to help and enable its ability to review and license non-light water reactor technology. Melchor and the code capabilities we're putting in and actively developing with Melchor is really driven by essentially a strategy under volume 3 of this analytical tools IAP for non-light water reactors, focused on accident progression and source term modeling. There's also a follow-on volume 5 focused on the use and development and demonstration of the use of Melchor for not just the analysis of a nuclear reactor under accident conditions, but various facilities across the nuclear fuel cycle under accident conditions. And so basically Melchor is really kind of evolving. It's really not just, if you will, a light water reactor code anymore. It really is kind of a bedrock code, a bedrock set of analytical capabilities that are critical to understanding and evaluating the potential implications from a public health and safety perspective of new energy technologies. And so we've been operating under this volume 3 and volume 5. And to go back to that earlier discussion, to make this real, to enable us to meet the timelines that the NRC is looking at, that the industry is looking at for deployment of non-light water reactor technology, be it 2020s, be it 2030s. We don't have a lot of time necessarily to, shall we say, reinvent the wheel. And so we're really turning around and harnessing the commonalities in across nuclear energy systems, the common physical processes across nuclear energy systems that are already embedded largely because of light water reactor development over the past 40 years. And we're moving and applying them to non-light water reactor systems with some targeted changes, some targeted additions. Obviously, we needed to add models related to Trisome fuel. Obviously, we also need to add some additional models related to metallic fuel and metallic fuel degradation as SFRs, as well as the sodium behavior for molten salt systems, similar thing, but with examples of, now we've got flowing fuel, for example. So we're taking what is a common framework, a common framework and a common set of analytical models for really similar physical processes, and then just targeting the development to very unique aspects of these systems so that we can enable in the short term innovation. This is just sort of a lot of our work. So this isn't just, and it's important for me to say, this isn't just me talking right now, that this is wishful thinking. The code is actually really starting to sing, surprisingly. It seems it's happened rather quickly, actually, in my view. Last year, we had 3 public workshops to demonstrate MelCore capabilities for heat pipe reactors. We put in models specific to heat pipe reactors, to demonstrate models for gas-cooled reactors, and then also the pebble bed molten salt reactor. I'll try to summarize some of the key things from those demos going forward. But we actually, these are real demos that we did last year, and the code's actually really calculating real numbers. And we're actually, Casey Wagner at Sandia was instrumental in a lot of that model development and a lot of the analysis for that. Brad Beatty at Sandia has been instrumental in a lot of the work, the development work, and a lot of the modeling work in MelchCore. In 2022, we're now looking at molten salt systems, that is the flowing molten salt system, and also the sodium cooled fast reactor. We're looking at public meeting demonstrations in the summer of this year. So none of us are sleeping a lot, but anyway, it's really kind of an exciting time for us because we're actually developing and actually demonstrating real safety analysis capabilities in the near term for these systems. Let's see. This is just sort of a highlight of some of the key areas where we've sort of put or added features into MelchCore. I just wanted to drive this home a little bit more. From a control volume hydrodynamics perspective, our thermal hydraulics, really what we had to do for MelchCore primarily were things like generalizing the working fluid treatment, adding in equations of state, that is, shall we say, steam tables for non-water fluids. We've also added, and this is under development, but it's actually, it's not in the latest release, but it is in the code, conduction heat transfer within working fluids. That is, if I've got a sodium system, we are now treating conduction heat transfer within the actual working fluid. It didn't matter for water as much, but it does for sodium to a certain extent. So we've also added in specific models related to convection, and flow models that through, say, packed beds of pebbles, for example. In our core models, like I was saying earlier, we've added additional features to actually treat fuel that isn't just a rod, but is actually a trisome particle to treat its heat up, and also the diffusional fission product release from that type of fuel. We've added a special component to treat heat pipes in the code. We have graphite oxidation modeling, and obviously we have a range of specialized conduction models to treat the new types of geometries in these reactor cores. We are currently actually enhancing some of our core degradation models specific to sodium fast reactors right now, and the treatment of metallic fuel degradation. Our fission product release modeling, again, like I was saying earlier, we have a generalized fission product release model for metallic fuels. We do treat through solution of essentially a diffusion equation, the transport of fission products in trisome. We also have added in, and this is what I was saying earlier, Mike, we have added in essentially a new model, we call it GRADER, the Generalized Radionuclide Transport and Retention Model. That's thanks to Fred Gelbart, who's been developing that model at Sandia with us. We couldn't find something that gave it that made it greatest, but it is GRADER. And the idea there is that we want to look at how fission products actually chemically interact with new working fluids like molten salts and sodium, and potentially stay bound up in those fluids as opposed to getting released into vapor spaces or atmospheres, and more able and then become more able or more mobile to be transported into the environment. And then, like I was saying earlier, we have done some simplified neutronic modeling as well with point kinetics. And again, the primary goal there is really to understand the broader spectrum of accident scenarios. We're not everything is a LOCA anymore, not everything is a station blackout. Some of these new types of systems may have lower safety margins when it comes to reactivity, insertion accidents or loss reactivity control accidents. And so we have those capabilities in there now too. This is just an illustration of our heat pipe reactor model. Really what we added in here, we're not doing, and this is again part of our philosophy with MelCore, we don't necessarily need to model all of the thermal hydraulic processes in a heat pipe, especially under accident condition. We really have reduced this down to essentially an overall mass and energy balance under accident conditions. We're not really worried about wick flows and capillary flows. We assume based on more detailed analyses that when you are in the right operating limits for a heat pipe, it is heat piping, shall we say. It is removing heat. You have sufficient capillary flow. When you get into an accident situation that pushes you beyond those operating limits, we then break down and we reduce to a mass and energy balance effectively. And it's overall simple. We illustrated the heat pipe model. We essentially used what was a candidate or a paper reactor out there for a heat pipe reactor. INL Design A, I believe, was the reactor. We identified for this type of system, one of the candidate scenarios we identified that led to conditions that were more severe was effectively a reactivity control event where control drums malfunctioned. And they basically spuriously rotated outwards. That led to a power increase, temperature rise. The temperature rise combined with degradation of heat removal on the secondary side actually led to pressurization of the heat pipes and potential failure of the heat pipes. That progressed into core damage and fission product release from the fuel. We were able to capture, after we essentially put in an artificial scram signal at a peak over temperature of 2200 Kelvin in the base case, but we varied it in uncertainty analyses. We were then able to look at the gradual cool down of the reactor through radial cooling, conduction of heat away from the fuel in the reactor out to the side of the reactor, if you will. So that for folks who have had experience with RCCS systems, the concept is basically that the heat in the reactor is essentially moving outwards to the side of the reactor, to the vessel, and radiating out into a confinement or a large structure. This is just an example of some of our calculations with this, obviously showing pressure excursions in the heat pipe, showing also the over temperature in the fuel leading to iodine releases from the fuel. This is just an illustration of the various failure mechanisms that can lead to new pathways for fission products to escape out of the fuel. Obviously, as the fuel heats up, you can diffusionally release out and release into the actual reactor vessel. If the heat pipe fails, there's the potential for fission products to escape into the heat pipe. And if there's any failure in the heat pipe to the secondary system, you can have a bypass event, which allows fission products to escape into the environment in that way. So we were able to, in a systems level, capture a broad range of of release pathways with the heat pipe. I don't want to belabor this one too much, other than to really just say that we're now able with Melchor to do detailed uncertainty studies. And I like to show blob plots. I don't want to belabor this, but basically this just comes from essentially 2,000 realizations of a broad range of scenarios where we varied effectively the time at which the reactor tripped. That is, when did our scram signal come in? And we were actually able to identify some interesting behavior across this. There were obviously other uncertainties too related to heat transport parameters, et cetera, conduction terms and convection terms. But we were actually able to see that there's an interesting bifurcation that actually occurred in these heat pipe reactors, in which you can get situations in which you actually don't necessarily fail. You actually have lower temperature fuel. It doesn't melt the heat pipe early, but it actually allows the heat pipe to pressurize and actually fail up to the secondary side. And there are also other scenarios in which you have a faster power ramp. It leads to fuel melting and fuel melting and melting of the heat pipe. So we're actually able to, with these simulations, capture some interesting bifurcations in accident progression based on the type of power ramp. Sorry, Mike.
Can I ask,
Yeah.
the figures are the same. The y-axis is different. The
Yeah.
peak ring creep versus peak creep. What is the difference?
So
Because they look the same to me. I mean,
oh, one's clad and one's fuel
Oh.
temperature. That's all. They basically run together.
okay, so that's the reason.
Yeah, yeah. You're essentially seeing here that for scenarios in which you actually get creep failure, you're actually sitting at fuel temperatures and clad temperatures that are actually quite a bit lower here.
So you sit there and just cook.
No. Yeah. Whereas if you pump heat into the fuel, you're not getting it out. When you go here, you get very high temperatures in your fuel that actually cause local melting and release. So it's actually, there are some actually interesting bifurcations that it can occur. And we only uncovered that through the ability to do these types of uncertainty studies. When we get into gas reactors and the fluoride salt cooled high temperature reactor, we also have now pebble systems, Trisome. This is just an illustration of how we conceptualize the overall process and modeling of release from a Trisome particle. We are able to represent a broad range of conditions with Trisome. I don't want to belabor this too much, but we're actually, in our models, we actually look at the diffusional transport of fission products in the Trisome through not just the fuel, but also through the buffer, the pick, and the SIP layers.
Can I ask a clarification?
Yeah.
The cartoon on the upper left, that's just the kernel.
Yep.
So
Yep,
you just
and then-
assume you've got umpty-ump of these things.
Yep.
And they all behave similarly?
Yep. Yeah,
Okay.
we assume that they all behave similarly within a core cell, effectively.
But so you're modeling the kernel.
Yeah, we're modeling the kernel, and then that couples into a source, if you will, for the matrix, which is the graphite pebble.
How do you then model the green?
The green is essentially just diffusion, if you will.
So just
through-
diffusion of the material through the green to the
to the
fluid.
environment, yeah, to the fluid. Right now, we haven't exercised them, but there are certainly there are partition coefficients that could influence, and we could use to model the potential for vaporization into the fluid space from the edge, but we haven't exercised that. We're able to model under, essentially for an intact Trisome, we model essentially the diffusion through all of these layers of the Trisome particle. When the Trisome particle fails, basically what we get back to is essentially we assume that those layers are gone, and then we just do a diffusional release out of the fuel into the graphite matrix, of the pebble. And then ultimately, all of that then gets out, as Mike was saying, into the fluid around this pebble. And there are obviously a lot of additional intricacies, but that's at the core. The key thing, though, is there are a few features that are important in that model. One is the failure. When does a sick layer fail? So if I go back here, you can see here that this is the concentration in the sick layer. It acts as a very key barrier to the movement of fission products out away from the fuel and ultimately out into the pebble and ultimately into the fluid. If the sick layer fails, then we're just essentially doing diffusion or release out of the fuel. Now you don't have any of those barriers that potentially impede or act as resistances to fission product diffusion. And now you're back to, I've just got fuel and I'm kind of migrating out at high temperatures. So that failure condition for the triso is very critical. It's fundamental to how much gets out. That's a critical parameter to worry about. That's a critical model to capture, is that under high temperature conditions, what is the probability of those layers around the kernel actually failing? That's one important consideration. The next important consideration in this model that comes out in terms of influencing how much fission product inventory actually escapes the fuel is actually the diffusion parameter, the temperature dependent diffusivity of fission products in the triso through these different layers. This is just the typical diffusion equation, and this diffusivity has quite an important impact on how much can potentially get out. What we often see, and part of the reason is that there is still, for some fission products, relatively large uncertainty, relatively limited knowledge about what this diffusivity actually is. And so this is an illustration when we had to go and actually model this for our demonstration calculations. And this is sort of one of the things that I wanted to bring up and emphasize here and kind of whet the appetite is that there's very little diffusivity data for a lot of the key fission products. What we did is we had a few fission products. We had some information from an old IAEA tech doc. We used that diffusivity. We assumed then that iodine essentially behaved like krypton. It was just an assumption. And then for other fission products, what we did, because we didn't have a lot of information beyond these key fission product species to populate this diffusivity, you think it's such a basic thing, but we actually have such limited information here. What we did is we essentially determined a diffusivity for the other fission products based on how they scaled for LWR diffusivities to cesium. We knew what cesium was. For all the other ones, we just essentially scaled that the other fission product diffusivities to match the scaling factor for LWR diffusivities to cesium. And that's where we were able to get. And it's not that there's a limitation in the code so much. This is reflecting a fundamental knowledge development that we still need, if you will. So, and this gets back to that point. Sorry, please.
Oh, yeah, so I was just wondering, I don't know too much about Triso, but how does this like vary, or does it vary a lot depending on like the burn up of the fuel? Like,
yeah. That it does. That the data that we have actually, we've seen orders of magnitude difference in diffusivity from an irradiated to an unirradiated. And that's a really, really good point. So one of the things that we haven't explored, but that we really actually want to, is imagine you've got these pebbles cycling through the core. they come in from the top, if you will, and they're cooler, they go down, they get hotter. They also get more irradiated as they go through. So the cycle and how they are cycling through that core is really critical to determining the conditions from an irradiation perspective and from a temperature perspective. So typical irradiance form, it kind of temperature matters for diffusivity. So you're now very sensitive to, under just steady state conditions, low level releases can be very interestingly reflected or influenced by how you're representing the fueling cycle, how you're representing the temperature, the time that pebbles sit at high temperatures. In some of our calculations, if you just assume very high diffusivities for irradiated particles, say 1,000 days of steady state operation, you could find, under that very naive assumption, that 0.1% of your cesium migrates out in a steady state condition. It's a non-negligible release, and that's assuming basically that your particle is sitting at high temperatures
All
for
that
all that time, and it's fully irradiated. So it's not reflecting any of its irradiation history or any of its temperature history completely. And so there is an interesting, and it's a really great point, because there is a very interesting feedback that we haven't really explored on that topic there from a systems level operational perspective. So anyway.
So does that,
Yeah.
just to kind of follow up on that, so especially like say where there's this extensive data, say on silicon carbide, especially as something that we know, the diffusivity that covers a large range of burn up or DPA for silicon carbide itself.
Not necessarily.
Because I wouldn't, I'm just like, would you expect with the silicon carbide, something that's the primary barrier that has really good performance?
Yeah,
that degrades significantly with DPA.
it does.
Okay, and is there any, like, what are the rough estimates of like how much worse does it get now that, you know, if I start forming woods, et
I
cetera?
didn't put that graph up there, but we kind of saw a few orders of magnitude.
Okay.
Yeah. So for example, if we were to assume unirradiated conditions, very little escapes under steady state operation. It's kind of in the noise. When you're assuming very irradiated conditions, very, very damaged particles just sitting there releasing them, we actually found over long operational time frames. And this is not reflective of the operational strategy or the actual fueling behavior. We found numbers on the order of 0.1% of your cesium inventory kind of popping out. So it is quite dramatic, the impact that we can see. And this is a key uncertainty, a key area of knowledge advancement. And it goes back to, it's not so much that our discretization will change this entirely. It goes back to just a fundamental physical phenomenon and the knowledge gap. And the reason that I wanted to maybe just kind of belabor this point a little bit is that I think it's fundamental from our perspective. How do we drive innovation? So we're going to, oh, sorry, Mike.
So I have 2 points. One is we're 10 minutes to the end.
Yes, I know.
I'm unfortunately the timekeeper. But
That's okay.
Now that I said that, now I'm gonna fail my. So there was an old model called Parfume.
Yes.
Is this,
It is.
is this from a physics standpoint, is this Parfume
It is.
implemented into Melchor?
It
Okay.
is. Thanks, Mike. Yeah, it is. It is. But so it's nothing dramatic, but
That's fine.
in that
I just want to
regard,
make sure I understand.
absolutely, no, absolutely, yeah. But what it is that it's not so much maybe the discretization, the fidelity here. It's our knowledge gaps, and we're going to have increasingly a lot of knowledge gaps for our non-LWR technology in these types of areas. So a broad range of knowledge gaps. Our question is, if we're going to help and drive innovation and drive decisions related to safety and licensing decisions in the end, we need to provide those capabilities to better understand which areas of knowledge need to be closed, need resolution. And so that's why we've done, if you will, we focused a lot on a broad range of uncertainty analyses. I didn't want to belabor this too much, other than to really make the point that for us, using Melchor, our focus isn't so much on getting the better answer for these systems. It's being able to probe things. This is the RCCS system. How important are various characterizations of performance or potentially safety system performance degradation? How important is that to overall estimates of safety and risk and the performance of these systems? And so we focused very significantly over the past year on trying to figure out and trying to illustrate the capabilities of these codes in these situations. This is just illustrating here, peak UO2 temperature. Whoop-de-doo, it's heavily influenced by graphite thermal conductivity, not surprisingly. The other metric that I wanted to point out here is that you can see here, this is some single realization cases. This is a typical heat up and cool down transient for a high temperature gas reactor under a pressurized loss of force circulation. The fuel heats up, and then with time, as the decay heat drops, it's able to move that heat out through conduction and radiation to the side of the vessel. And ultimately into the confinement structure and and rejected ultimately through the RCCS. And then with time, and we're talking days, so this is a 72-hour, 3-day transient, things start to cool down. They start to slowly come back down, unless you assume some very significantly degraded conditions for your heat removal, in which the temperature just never turns around. And so one of the metrics that we explored in our uncertainty studies, yes, there's peak temperature, that's great. But one of the things we also explored was, do you actually arrest the accident in, say, a 80, 100, 150 hour transient, if you will. And so what we were able, so this is just an illustration of to show how degraded does our RCCS system have to be before we're just not really able to turn that accident around. We're not able to keep that heat removed. And the reason that we brought this out and isn't because we just wanted to vary parameters like crazy. That's fun. But the reason we brought this out, and this is a fundamental question, is that these passive systems are really cool. They're really great from a certain perspective. They're very reliable overall. Where they may not be, or where there may be interesting considerations, these passive systems, and this is often what you see in nuclear safety, nuclear energy safety, is that sometimes our perspective and how we view safety philosophy is somewhat of a Monday morning quarterbacking. We had an event, and then a lot of people go down a particular path, and their safety philosophy and how they evolve and design safety systems for new technologies is influenced by what they know. One of the things that we certainly with light water reactor technology, they're very, from a perspective that we have a lot of active systems, we have pumps, we have valves, these can randomly fail, and that can contribute to overall failures. It requires you add redundancy, you add complexity to your plant to mitigate the potential for that random failure actually having a significant risk impact, if you will. Passive systems are potentially really good because they eliminate or they potentially reduce significantly that potential for a random failure, that is a pump stops working or a pump doesn't start up, to contribute to an accident scenario. However, you're now moving, how does a passive system degrade? Under what conditions can it degrade? Can I throw debris on it? How much pigeon gunk or whatever it is fouling up the heat exchanger do I need to worry about? What is my actual safety margin now for these passive systems, and how degraded do I have to be? And so that's what we were really exploring here is with the RCCS performance. How degraded do I actually have to be before I get into trouble, for example? And it's starting to, what we want to show here and understand is what is that safe operating envelope. And so it's a very we're trying to interrogate the behavior, we're trying to interrogate the performance of these systems and how much range there is, how they can respond to accident conditions beyond just random failures, to seismic events, flooding events, high winds events that throw debris all over the place, malicious events. And so this isn't perfect, but to me, this is the fundamental, if you will, frontier of nuclear safety going forward, especially with these systems, is how do we characterize safety now, and what are the ways that these systems can fail? So I don't want to go belabor this too much, but I will quickly just finish up and quickly say that we have added in a model called Grader to represent fission product transport, fission product behavior, and retention in molten salts, sodium, whatever working fluid. So one of the benefits and one of the potential improvements of these systems is that things like molten salts, they're purported to be sponges almost. That is, if fission products get into them, because of the chemical interactions between those fission products and the salt or the fluid, they are now more bound up, if you will. They tend to stick to the salt and they're not as able to get out. However, these fission products, some fission products are highly soluble, some aren't as soluble. They have a range of behaviors and vapor pressures and potential to vaporize out of salt that varies with temperature, varies with things like oxidation state, etc. So we're building in a model right now that captures essentially all the key degrees of freedom associated with characterizing how fission products migrate through molten salt or sodium systems. That includes burnup depletion calculations, isotopic state transitions. It includes space, essentially hydrodynamics, the advective motion of fission products through a fluid. And finally, the physicochemical state, that is cesium fluoride, or is cesium more likely to be bound up and stick into the salt as a cesium fluoride, or is it more likely to sit there as a colloidal or a non-soluble fission product that can potentially be released? I don't want to belabor this too much, but basically it's really just we've really got it down to actually being able to calculate the release of fission products. And again, here's the fundamental issue, the fundamental gap we're having, is that to be able to calculate solubility, vapor pressure, and salts of, say, cesium in these fission products, we rely on thermochemical information. That information is actually very poorly known, very sparsely known right now for a lot of conditions, unfortunately.
So you've got to have basic knowledge,
Yep, again.
or basic thermochemical knowledge.
Yep.
So with the molten salts, how much of that, is there much available from the fuel reprocessing side of things that know about this? I would think there'd be a good amount from, plutonium production and fuel reprocessing that would be known about molten salts.
There is, but there are actually significant knowledge gaps, especially as you get up into temperature. And we
Okay.
actually don't know for a lot of the fission products. For example, the thermochemical databases right now that we have access to may not have a lot of information about iodine in these salts. There are experiments, but they're not necessarily compiled entirely. So anyway, thanks, Mike. I know I'm at the end. Yeah, no, this is perfect. This is perfect. Yeah.
So I've got a follow-on question here. I see a lot of the gaps and the uncertainties that actually comes from that we don't really know the materials, right? Say their properties at normal operation and higher burnup, right? And my question is that, so we see a big gaps here from Melchor and the programs, and how this kind of need or communicate with DOE or other programs so that these gaps will be filled in?
So we are actively working to inform experimental programs to communicate our knowledge gaps and to make data requests. If
Right, as
we-
a material scientist,
Yeah.
we will be happy to fill in some of the gaps, but we want to know what are the mechanisms that we can work with project like this.
And so, for example, the molten salt reactor campaign has areas particularly focused on that. The NEAMS campaign has areas particularly focused in these areas. And I think there's a fundamental need here. The question we have, for example, on this one is, are we going to be able to do all the experiments we need and the broad range of experiments across temperature conditions, fission products?
For 3 new foods.
And so the challenge is, and this is where I think it's very much an open question, can we apply atomistic modeling, DFT, molecular dynamics to better understand or better calculate the phase diagrams for these systems, but most importantly, basic things like vapor pressure and solubility. That's really what influences us here. And I don't know if there's been a lot of, there hasn't been a lot of initial effort here. To be honest, I think it's still conceptual, but I think it's a very important potential area. I think the challenge we're going to have with the application of those techniques in this realm is the question of credibility. How do we show that those techniques are appropriate? How do we, quote unquote, validate them in these applications where they've never really been fundamentally used before? There's a lot of experience in these techniques in other areas of material science for sure, and certainly material performance. But when you start to get into accident conditions, we don't have a heritage, if you will, of actually using these techniques in a manner that can pass through, say, regulatory scrutiny with, frankly, individuals who may not be very familiar with quantum mechanics, even. So, yeah.
I guess going on the regulatory side, how do, I guess, these severe accident codes, MeltCore, I guess, who's the customer? Is it the NRC and also the reactor companies? I guess, for other things, they kind of have to have their independent codes. Do both folks use MeltCore, or they have to have their own code for that too?
So that's a great question. In the past, we did have separate codes. Oftentimes, vendors and regulator would have separate codes. The modular accident analysis program was the industry sort of severe accident code. MeltCore was the regulator's severe accident code. We're not in a position where we're restricted in that way anymore. A code can be used by the regulator, and it can also be used by vendors to prepare their safety case. NewScale is an example.
That's the best example.
Yeah. Okay. They did their PRA essentially with MelCore, and it's a great example. Again, the fundamental question isn't necessarily the code; it's the use of the code, the accident scenarios being analyzed, the assumptions, etc. in that analysis, the uncertainties, were they adequately considered, and all of that is subject or open to regulatory review and scrutiny. And that's where sensitivity calculations can be very important. Sorry.
Very good question.
I'm gonna give us one more question, then call it a.
No, please.
That's all right. Go ahead.
Yeah, is this a controlled software or is open to?
Oh boy.
I'm laughing because I've spent 2 weeks to try to get permission to use the new version.
Okay, that
Sorry.
answers it.
It is part 810. It is controlled software. So typically, if one is in the U.S., a permanent resident, a U.S. person can use it, or if the individual is from a country that is a member of the Cooperative Severe Accident Research Program.
Yeah, so there are certain countries that are part of
Yeah.
the NRC group of
Yeah.
users,
Thanks.
and that's allowable. Or because as Dave has said, you have to go through this and get permission for the users person by person, individual by individual.
Yeah.
Thank you.
Thanks.
So it's just like all the stuff you have to go through for your tools.
Exactly.
Oh.
I was hoping not the case.
Last question, otherwise I'm gonna thank Dave and,
Thank you, guys.
thank you very much. You know how to shut this thing down here?
Exactly. Right.
Yeah. All right, so everyone online, we're gonna be closing out, so thank you for attending.
You've got multiple phones.
Yeah, don't ask me.
That was cool talk. Thanks for
Thank
giving
you.
you.